In the name of God, the most merciful, may the peace, blessings, and mercy of God be upon you. We will start a new subject by God's will, series of lectures about selected topics of mechanics of materials. We will talk about Macaulay's function, but first we will discuss the step function. There is a function called the unit step function or Heaviside function that starts after a certain time when we plot t as the x-axis and the Heaviside function as the y-axis. We can express the relation as ht minus a equals 0 for t is bigger or equal to 0 and less than a but equals 1 unit when t is bigger or equal a. It forms a step shape with a riser equal 1, which is extended for values of t bigger than a. In the upper part of the slide, we can see a line graph, which we are familiar with. When a line of positive slope m passes by 0, 0, the point 0, 0 point, its equation can be expressed as y function equals y equals m by x. If the same line was shifted by a distance a from the y-axis and maintains the same slope, then y is expressed as y equals m multiplied by x minus a. But when the line is shifted by distance a from the y-axis and maintains a negative slope minus m, the equation can be expressed as y equals minus m multiplied by x minus a. This expression we will utilize later when dealing with triangular load. But the y-axis will be w of x, and the load expression is written as w of x equals w over b multiplied by x minus a, where b is the base of the load and w is the ordinate load intensity. We have conclusion that function apart by distance a from the y-axis is expressed as f of x minus a. But if the slope is 0, the line becomes a horizontal line apart from the y-axis by a distance a. The line can express a uniform load starting from a distance a from the left edge and extending to the end of the beam. Its equation will be w of x equals w by x minus a raised to the power of 0 to include that the load at x minus a is considered 0, while for the values of x bigger than a, it will be equal w. In the next slide, if we have a beam with length L having two supports and acted upon by a concentrated load P at a distance A from the left support, and the remaining distance to the right support is B, we can estimate the reaction at the left support. It will be equal to P multiplied by small b divided by L, while the reaction at the right support will be equal to P multiplied by A divided by L. To express the shear function by using step function, we can consider the previous beam as an assembly of three step functions. The first case is the shear from the left reaction force and expressed as Q of x equal to plus b multiplied by small b divided by L in the form of a step function with a rise equal to p over L that extends to the end of the beam. To express the load P as a shear function, it also acts as a step function starting from a distance A with a rise of minus P and extends a distance of L minus A. Finally, the right support reaction with a value of PA over L is also a step function that starts from X equals L with a shear value of minus PA over L. The previous shapes can be combined to form the shear diagram as shown. In the next slide, quoted from Professor Timothy Philpot's book, An Integrated Learning System, Macaulay's functions represent quantities that begin at point A. Before point A, the function has a zero value. After point A, the function has a value of f of x minus a raised to the power of n, since it is shifted by a distance a. Macaulay's function is expressed not by the parentheses, but with a different form, smaller than, bigger than, signs, or bracketed terms. The function value is 0 when x is smaller than a and x minus a raised to the power of n, or x bigger than or equal a. In the next slide, the Macaulay's function deals with three values of n, as n equal to 0, n equal to 1, and 2 values. When n equal to 0, the function is a straight line, and the y value equals x minus a raised to the power of 0 equals 1. When x equal a or bigger than a, and 0 for x. Macaulay's function with n equal to 1, the function is expressed as inclined line, and the y value is x minus a raised to the power of 1 equals 1 when x equals a or bigger than a, and 0 for x equals 0. The last form is when n equals 2, when x minus a to the power of 2 expresses a parabolic plot. In the next slide, we can see new functions that are called singularity functions when n equals minus 1 or n equals minus 2. These singularity functions can be used to express concentrated loads and concentrated moments. These functions can give the value of the load intensity in the case of concentrated load B naught acting as W of x equals B naught multiplied by x minus a raised to the power of minus 1, as equals 0 when x does not equal to a, and equals B naught when x equal to a. In that case, n equal to minus 1. In the case of concentrated moment m naught acting, the load function expressed as W of x equals m naught multiplied by x minus a raised to the power of minus 2, as equals 0 when x does not equal a, and equals m naught when x equals a. The n value equals minus 2 in this case. In the next slide, there are two graphs. The first graph shows the relation between W of x and B naught by x minus a raised to the power of minus 1 function shifted by a distance a, while the second graph shows the relation between W of x and m naught by x minus a raised to the power of minus 2 function shifted by a distance a. In the last slide, there is a difference between the integration of Macaulay's functions and the integration of singularity functions. In the case of Macaulay's functions where n bigger than 0, after integration we add 1 to the n and divide by n plus 1. In the case of singularity functions where n less than 0, after integration we add 1 to the n and there is no division by n plus 1. Thank you, and peace be upon you all.